Yes, thank you very much, and thank you for the invitation to participate in this nice workshop. I will present today some results on the stability of waves with constant vorticity obtained at UEA with my colleague Mark Blyth from there. So I've probably seen these things this week, or people talk about all of this stuff. Just a very short introduction. The stability of water waves started probably with the works of Benjamin and Shear, and in '67 when they found this modulation instability of the Stokes wave, and we around the same time obtained some analytical results on the same thing. So and then a large number of people have a look at the stability of just gravity water waves. And again, here is a list of names which is not comprehensive. So probably the curve should be mentioned with the derivation of cubic nonlinear Schrödinger equation when he looked for the long wave instability of the weakly nonlinear waves. And then various people extended this to 3D or to finite depth, like Benny Rosk or David Stevenson. And then, so this is again more deriving weakly nonlinear equations. People started to look at the stability of numerical stability of these finite amplitude waves, and probably should mention Longe-Higgins here when he looked for the superharmonic or subharmonic 2D perturbation of Stokes waves. Tanaka at the same time obtained some results, and then McLean looked at the 3D perturbation of in deep water and finite depth of the water waves. So those works are mostly numerical. Some theoretical results obtained by McKay and Safman when they look at the condition of instability, this story about the Krein signature of collision of eigenvalues. And then Tom Bridges and Milke, they have a theoretical proof of this Benjamin field instability. And then, as I say, in the more recent years, there is a flurry of forks on this. People he mentioned here, like Vera Hoover, some of the people are doing it even like this year or last year. So they do numerics based on different methods, the so-called AFM method or the other methods. So say this is not comprehensive, so I'm sure I missed a lot of people who should be there. So moving from gravity, so people look to see what happens if you put surface tension on the water waves, and there is again a number of works on the stability of gravity capillary water waves. Again, mentioning here just probably Kawahara and the Georgievich and Redekov for some analytical results or weakly nonlinear results, and then Zhang and Melville for some numerics, and then more recent Bernard and Olga Trichenko in some numerics using again the AFM method. Okay, now in my talk I actually remove gravity, so I'm trying to see what happens if you remove gravity. So looking at just pure capillary waves, so the so-called Crapper waves in infinite depth. Or Kinnersley in finite depth. So we have work by Hogan who look at some superharmonic perturbation, and Chen and Safman subharmonic, and then Roxana Tiron and Weong Choi, they revisit these problems, and they look properly at all this subharmonic instability using a conformal mapping method, which will be similar to what we'll see today later. And then my colleague and myself will look for like what happens in finite depth with the so-called Kinnersley waves. And the last work is by Sunao, Morashige, and Weong again, when they look at 3D weakly 3D perturbation of 2D capillary waves, the stability of those ones. So that's again with no gravity. Now actually moving towards what I actually do today, waves with shear flow. So after people look at for a while at gravity waves and the computed solutions and the stability of them, they start to put a vorticity on the water, and then they computed traveling waves, and again there is a list of non-exhaustive list of people from there, and there's some typos as well in the name of Konstantin, for example. And so there are lots of people computing these waves, and they have the waves which finish in end up in 120-degree singularity, or the waves which are overturning depending on which way is the vorticity going. And so the natural question was next, what happens if are those waves stable or not? So some people started to look numerically at those gravity waves on a linear shear current like Okamura and Oikawa. And then Francis and Karif again have come back to these problems, and again they compete with some analytical results. And again, Sunao and Wu Yong have looked at these problems using a conformal mapping. So again, our work will be sort of using a method in the spirit of Sunao and Wu Yong. Now, what happens if you remove gravity now from this problem? Well, the first and amazing thing is that you actually can obtain exact solutions. So, and that was obtained numerically by Vera Hoor and Jean-Marc van den Broek in the 2020 paper, and then later the same year confirmed by Miles Wheeler and Vera Hoor. So you find out on the surface the waves is exactly as the Creper waves, the one which finish in whatever overturning bubbles, overturning waves, and enclosed bubble. So it's simpler to analyze the stability of those waves because they have exact formulas in some sense for the basic wave. So that was our goal, to try to see if we can look at the stability of those waves with constant vorticity, which are given by exact formula or Creper waves. So again, I should mention this very funny connection because again, Creper waves is surface tension of vorticity, and actually you can find out the same waves on the surface for vorticity, no surface tension. Obviously, inside the flow, the situation is more complicated. So what I'm gonna tell you, I'm gonna talk today about in the next, I don't know, 10-15 minutes. So that's my problem. So you have an inviscid incompressible fluid of infinite depth. Again, yes, so infinite depth is a funny thing when you have vorticity because you can have an infinite speed at the bottom. But again, you can put finite depth if you want, but then you lose this exact traveling solutions. So anyway, so you have an infinite depth, fluid depth. You have a constant shear. No gravity. You move, I guess, to the right in this figure. You assume you're moving with a frame of reference with a wave. You introduce the stream function as you do in these cases because you don't have potential, and your stream function will satisfy this condition. So the Laplacian of psi is minus omega, the shear. You can introduce a so-called shift stream function, which actually has this nice property that is actually satisfy Laplace equation by taking away this omega y squared term. And then you can define a harmonic function, which looks like potential, but is not, which satisfy the Cauchy-Riemann equations between phi and psi. So the problems to solve actually today is to find out this phi, which satisfy Laplace equation, and these boundary conditions, kinematic and dynamic. And I wrote boundary conditions in this form because I actually want to allow waves to overturn. So, and in this case, B is whatever, some Bernoulli constant. So, as usually for these problems, the trouble is that you have an unknown domain and so on, and nonlinear equation and nonlinear conditions at the surface. So the easiest, one of the methods is to reformulate the problems as a PDE on a fixed domain. And then we use this conformal mapping method used maybe by Diachenko and some other people, and Wu Yong more recently for waves on a linear shear. So basically, you move from a domain with a unknown surface to a fixed domain with this conformal mapping. The free surface will correspond now with the whatever eta equals 0 term, so the boundary of the domain. And then you have to find this conformal mapping, obviously, and then we can introduce the surface variables only. So you manage to go to problems only on the free surface, on the surface. So after some algebra, you have a couple of equations, phi t and yt. Tilde comes from the fact that they're on the surface. And then you have whatever is on the right-hand side, including the Hilbert transform H. Again, psi is the parameters which parameterize your free surface. B is our previous friend, the Bernoulli constant. And you have a link between x and y and phi and psi. So actually, you're going to remove two of them later on. So as I say, the main thing of the, which kind of motivated us is that actually have a exact form for the traveling wave in this case, shown by Vera, Hur, and Miles Wheeler. So X naught and Y naught are the parameterization of our traveling waves of the free surface, depending on psi. So this is the things you probably recognize from the Kuiper waves. So and the links between A and omega is given by whatever, some relation here. And if you're familiar with this stuff, so basically you start with waves which are sort of small amplitude, and then increasing A, you just go to this sort of waves which self-intersect. I should say that Vera Hur and Sergei Dyachenko, I think Dyachenko, the son, have obtained solutions going higher on these things, but they don't have an exact formula. And they have some gravity, and then they can take gravity zero. But so we just stop at this point when the solutions self-intersect. So again, if you really want to see that, that's the branch of solutions going from zero amplitude to somewhere. And then omega is some non-dimensional shear. And I should say that again, the surface is the one given by Kuiper solutions, but inside the flow, it's slightly you have other things. So you have some psi naught given in this form, y naught square, and then you have phi naught, which is related by a Hilbert's transform. Okay, so that's the what other people have obtained. What we have done, we perturb this steady state with x1, y1 quantities and so on, and then linearize the previous equations, which I'm not going to give here. So you have a bunch of linear equations, and then you use, as usual in these cases, you use Floquet theory, for example, and you expand your perturbation. I mean, you write the perturbation in this kind of form. When a sigma t, will give you a sigma, which is the eigenvalue. This p, it's this Floquet parameters, which is well, usually between 0 and 1. You can restrict it there, and then you just all of this have this sort of Fourier series, all of these variables. So you put this stuff in the linear equations, and you obtain. In the first case, you look at the stability of the waves in the zero amplitude solution, which we have like a flat state. So that's what you obtain. So you obtain a quadratic which you can solve, and then you have these two solutions for each n and p. So you may observe that the difference between one and the other one is more or less plus minus 1, which means that you always will have double eigenvalues. So that's a kind of big difference compared to the cases when you have gravity on this problem. So that's one of the things. And then you can actually, so that's, you get doubles for superharmonic, also subharmonic. So superharmonic again is the one, the perturbation is the same wavelength as the Bayes waves, and subharmonic the one which are longer. So you always have doubles, just jump from n plus 1 or minus 1 depending on n positive or negative. And also you have a quadruple at 0, which is not doing too much for our problem. For subharmonic, again, the double you get it anywhere, so it's the same double from here. You can see it from this one. If you just go plus minus 1, you obtain the next one or the previous one. But you also have a triple set of triple eigenvalues when n equals 0. So you don't have simple eigenvalues on the axis. So all of them are imaginary. So at 0 amplitude, it's sort of similar as other water wave problems. They're imaginary, but the main difference is here is that those ones are all of them doubles or triples or so on. Okay, so that's the stability in the zero limit. So the next we'll look at some asymptotic results. We assume that our A, which is sort of the amplitude, not exactly the amplitude, is anyway, you can parameterize the amplitude of the wave. So you assume first that A is small, and then you expand your base state like that, exactly, because you know x naught and y naught. You can also do the same for psi naught and phi naught, and also for omega. So now our eigenfunction system is something like that. Put that back on the linear system, and you have to solve a problem like that when L and sigma depends on A. And then you can expand actually L in terms of A and U and sigma. So our goal, so sigma naught is the imaginary whatever, double or triple. And the sigma 1 is the first order in this perturbation. And the question is it real or imaginary? To see if it's stable or not. Either around, if it's unstable, if it's real, or and so on, positive. So, okay, so this is, again, I should say that we can do this easily because this is actually exact solution. So you expand this and then you collect at each order the terms, classical perturbation theories. You obtain at this leading order exactly the problems from the A equals 0 case. I should just say that this operator L is composed from various terms like differential operators, Hilbert, and Hilbert of differential operators. And here A, B, C, D are sort of matrices 4 by 4. And then if you do the L1 things, you'll have a similar form, but the matrices will depend on psi. So that's the difference. So the next order, or the order A, you obtain this formula. And this, to have solution for this one, you have a solvability condition. So that's, again, using some operator theory and free-form alternative. So the right-hand side of this have to be orthogonal to the null space of the adjoint of the operator on the left-hand side. So you can calculate the adjoint and so on. You can calculate the basis for various eigenvalues. I just should say that sort of recent, I also seen similar perturbation methods used by Ryan Creedon, Bernard de Koning, and Olga Trishenko when they look for stability of some Stokes phase. And again, so now and Wu Yong when they look for weakly 3D perturbation of capillary waves. So they kind of use this kind of theory. They even go to the higher order, but they say that first order is enough for us. So you do some algebra, you compute all this basis and stuff, and adjoint, dot them with whatever the left hand side, right hand side, and you do obtain that for double eigenvalues, whatever, if p is 0 or not, so whatever is superharmonic or subharmonic, you do obtain that the first perturbation of sigma naught is actually real. So you have two of them, which whatever, one positive will give you instability, and for the triple one, you also have sigma 1 to be real. So the sigma 1 is for n equals 0. So the conclusion is that the waves are always unstable for a, whatever small a is, which again is kind of different from the classical problems when you have gravity, or even when you have capillary, or a combination of those, or gravity with shear. So by the way, I'll talk a bit later. So that's the main conclusion after doing this asymptotic analysis. So next, to confirm this one, or whatever, to check, we do a numerical analysis. Okay, we compute waves using a numerical method, and then there's just some classical theory, just to get this series of ANs, BNs, CNs, DNs are plus minus n. You actually can replace AN as a function of BNs because you have these links between them with a Hilbert transform, and the same for CNs and DNs. So you just get rid of two of those, like AN in the end, and you're left with BNs and CNs. You introduce the same number of collocation points you need, and then you evaluate those linear equations at these collocation points, and you obtain whatever 4n plus 2 in this case equations with 4n plus 2 coefficients which you need to compute. So if you can write this in this generalized eigenvalue form, eigenproblem, where A and B you can calculate them analytically, but we prefer to do it just using a method of impulses. Basically, just put one of these to be 1, and then go on the linear equations and find out the columns at each point. And then you solve this one, and then that's done. So that's say the classical sort of method, but just a reminder for people who may not be familiar. So this is sort of the first result I want to show. So in these graphs, we compare analytical asymptotic results based on this perturbation method and the full numerical results. So more or less the same graph left or right, but the different scales. So this one considers around 0, and this one is the same things but for bigger than 0. So let's see, for example, what happens when you have a small non-zero wave. So the amplitude is pretty small here, 0.001. The double eigenvalues, I just put the one for p equals 0, but all of them are double eigenvalues. They split in two, so you see only again half of the story. So because of symmetries of these problems, you should see stuff on that side as well, symmetric. So they split in two, and they go into the real. They have non-zero real stuff, real part. So the arrow that's kind of suggests they go from imaginary axis, split in two, and go in this sort of full circles. This is kind of if you want superharmonic stuff. And again, if you increase a, this one will go there, and so on. The asymptotic results are here with a triangle, and for the double ones, which are for roughly sigma bigger than 1, imaginary, and then here is for triple, for the circles. And then the dotted one are obtained just varying p from 0 to 1, and you feel more or less this segment between, let's say, 2 and 3, and that's the blue ones are the numerical ones. And there is a very good agreement, in our opinion, between the theoretical results and the numerical ones for both cases in this area. And again, you can see there is different sort of slope between them, because if you go in the previous page, okay, here you'll find out that you have a 2 square root of 2 here, and this is different kind of stuff. It's just 2 square root of roughly n, no, 2n or 2p. So that's the result. Now, again, looking at this equation, this graph. So what happens when you have gravity? So we try to put in some gravity in our code, which is not complicated. So go back again to whatever Sunao and Wong have done in the paper. So in this case, all the doubles split actually. So you'll have actually single ones here. And then when you for a small amplitude, they stay on the axis and they travel together and then just collide and then just maybe get off the axis and become unstable. But in this case, they're always unstable, whatever a is small, whatever small is a. Now the same story here, but at whatever I'm increasing sigma. And you see that the agreement between the numerical and the asymptotic start to deteriorate when a is increasing or when n is increasing. So when sigma 1 becomes too big or so on, probably have to go to sort of quadratic, which you didn't go, and then maybe that will have a better agreement. And now what you see here is a bit similar-ish with what, okay, not similar, we just look at the same phenomenon, but only for one eigenvalue. So on the left, you see a double eigenvalue, so just choose n equal 1 and p equals 0. And then initially, you have 0 real part. Increasing the amplitude, you obtain this sort of it splits in 2, again, according to this plus minus, according to the theoretical result. And then here, the full lines are numericals and the dashed lines are theoretical. And again, for small a, you have a perfect agreement. And then we start to deteriorate when it's increasing, which again, I assume if you do a quadratic, you're gonna get better. So by the way, so the imaginary part in our case has no contribution. The perturbation of the imaginary part is 0 at order a. So probably it's non-zero at order a squared. So that's why you have this quadratic stuff. And then similar things happens for triple eigenvalues. Again, for the small ones, it's doing okay, but then it starts to deteriorate when a is increasing. And probably the last graph. So those values are pretty small. So a 0001, 0005. And when you increase a, you no longer, I mean, you should have in theory these lines going whatever up to here, but they don't go. They start to curve back, and you obtain kind of bubbles, whatever, not bubbles, 8 figures, but they're different from what you see on the Stokes waves or in some capillary waves. So in this case, all these empty circles are actually corresponds to the superharmonic instability when we take n equal 1, 2, 3, and so on. And then when you vary from p from 0 to 1, you just feel the same between these empty circles. To obtain this circles of instability corresponding to whatever Benjamin Ferrer or some other things in for Stokes waves, you just vary from p from 0 to 1 and you obtain this nice circles. And then sometimes you obtain again these figure of 8 going back to the axis, and again you have some regions when there is no instability. Again, just the numerical stuff. So this is for a equals 0.025, and then you can increase a, and you can go actually to overturning waves. So I think we have like 256 points on this. Yeah, you can do it accurately. And then again, this kind of bubbles merge and so on. So this is for the smallest a, like 0.05. And then for the red one is 0.1 and so on. And the last one is blue, which is the so-called overturning wave. So the rate of the growth rates, whatever, for some given sigma are increasing as the amplitude is bigger. So the 0.45 is the limit anyway, so very close to the limit. So I think this kind of concludes my talk. So we've done linear stability for exact traveling wave solutions found by Vera Hoare and Miles Wheeler. So no gravity, just constant background shear. The main result is that waves of any non-zero amplitude are linearly unstable to both superharmonic and subharmonic perturbations. And then we've done this asymptotic expansion based on perturbation method and numerical computations, and we did some comparison between them. And thank you.
So any questions? Yes.
Thank you very much, Emilian. It was very interesting, very scary too, because I mean, there's so much energy in that basic flow. You know, it reminds me a little bit of Kelvin-Helmholtz instability. Okay. So I wonder if maybe the equations might be ill-posed. Is that possible?
Yes, it's a good question. Yes, I don't know. I mean, again, because you remove gravity, it's a bit, yeah, and physical, obviously. Yeah, so that's if you want, is a kind of limit of when you have a very strong vorticity, and again, if you go to the limit, yeah, the gravity is becoming less and less relevant, which probably. No, I mean, okay, so these problems you get it, like I say, you have gravity and vorticity, so you can increase vorticity and the gravity stays small, and at some point you assume the gravity is so small that it's zero in some sense. So in some, you can see like a limit of sort of flow when vorticity is increasing, if you want. So I don't know about this ill-posedness, so that's a good question. Yeah. So again, but being slightly unphysical, the whole. Yeah. I mean, yeah. That's. So as I say, in the last few graphs, we put some just a tiny gravity, and then you can see these things splitting here, and then they do whatever they do. They move on the axis and they collide, and they just get off the axis for finite amplitude, but not from the very small ones. So the things you expect.
Yeah.
You can ask question.
Pavel, can you hear me? Yeah.
Yeah. Can I ask a question?
Yep.
So this is Pavel Shnikov. Can I ask a question now, or somebody else asking?
Yes.
Yeah. Okay. So just to make sure, here gravity is zero, right? And when you just mentioned that you can add gravity, do you think that gravity can, at least for some amplitude, stabilize instability, or no chance?
Yeah, so if you add gravity, can you hear me? If you add gravity, then as I say, it does stabilize the problems for small amplitudes. So if you put more and more gravity, you'll have the regional stability growing, if you want, in some sense. So yeah, the answer is yes, you can stabilize it with gravity.
Mm-hmm. Thank you. And let me give quick comment. What you mentioned about that with Stokes wave here reduces to Kraper in some limits, and you mentioned this work of Hoare and Wheeler. I believe first result of this type was obtained by Sergei Dichenko, because I heard it's like 8 years ago already, when maybe 6 years ago when it obtained. I'm not exactly sure where he published, maybe with Vera Hoare or somebody else, but just make sure that he really was first to obtain this, that in the limit of large vorticity, we have reduction of Stokes wave to Kraper solution.
Okay, a second, I didn't know about the reference. Thank you.
Mm-hmm. Thank you.
Thank you. So maybe we can stop here. Thank you again.
Yeah.